go over a really simplified problem. Let's do just a rectangle. This side is x. That means this side would also be x. This side is y. That means the bottom would also be y. Let's say that the perimeter is this set 100 feet. And we're trying to find the maximum area. So area will just be x times y because it's a rectangle. Perimeter will just be 2x plus 2y, and that would be equal to 100. So this is just a simple system of equations. Let's try to solve for x first. So we would isolate y in this equation. So let's isolate y here. Y will be equal to 100 minus 2x divided by 2. We can simplify that even further. Plug y back into the area equation. The area would just be x times minus x. We can just distribute the x inside of parentheses. That gives us that area would be equal to 50x minus x squared. Then, since we're trying to find the max, we just do the derivative and equate that to 0. So the derivative of area is 50 minus 2x, and if we equate that to 0, x will just be 25. Now we need to find the y. So we know that 2x plus 2y is 200. So x equals 25.
Let's optimize a rectangle under a parabola. The length of a parabola is always going to be 2x because the height is going to be equal to y. That simplifies to 25 minus x squared. So therefore, we know the equation for a rectangle is equal to 2x multiplied by 45 minus x squared. We can expand this to get x minus. Okay, now we can just get the derivative to find the critical point. And x is equal to 50 minus 6x squared. We're going to find whatever this is equal to 0. Simplifies to therefore this is where our came back into length. Therefore our maximum area going to be equal to
today we'll be optimizing a cylinder and a sphere. So R is the radius of the sphere, and it's also the point at which the cylinder touches the sphere. So let's establish the radius of the cylinder to be x, and half the height to be y. replace x and y here. So we get pi x squared 2y is equal to b. Now we want to solve for a variable, so we're going to replace y using our Pythagorean formula. X squared plus y squared is equal to r squared. We isolate x. X is equal to the square root of r squared minus y squared. Because we move this here, take the square root. And we plug in this x over here, so we get 2 pi y of r squared minus y squared equals b. Now we want to take the derivative of this, which is, or first let's simplify it. 2 pi y r squared minus 2 pi y cubed, and that's equal to b. We take the derivative of this and set it equal to 0. So we get 2 pi y, 2 pi r squared, because r here is a constant, minus 6 pi y cubed, y squared, sorry. And that's equal to dv by dt, which we set to 0. So then we get 2 pi r squared is equal to 6 pi y squared. So we want to isolate for y, and we get r squared over 3 square root is equivalent to y. Because we move this here and we get 3 and then take the square root of that. Now we can plug this back in to our Pythagorean formula and we can solve for x. So here we get x squared plus square root of r squared over 3 squared, so that's just r squared over 3 plus, it's equal to r. And so x squared is equal to 2r squared over 3, or in other words, x is equal to the square root of 2r squared over 3. If we were given a numerical value for the radius, we can plug it back in to find x and y and the maximum volume of the cylinder. And that's how you optimize a cylinder and a sphere.
Welcome back to McGhee Academy. Today we'll be doing optimization of a rectangular prism and a sphere. We have our two equations set up. We have x squared plus y squared plus z squared equals r squared. These are with reference to the center of the sphere. So, the r squared value is from the center to the edge of the sphere, obviously. So when the edge of the sphere touches the rectangular prism, you have the equidistant point from the center to the edge of the sphere, which is r squared, and due to Pythagorean identity, which is in 3 dimensions, x squared plus y squared plus z squared, which is x, y, and then z is this way, would then be equivalent to r squared. So, using these values, we can determine what this equation would be in terms of x, y, and z. So, if we know that length is equivalent to 2x, we know that width is equivalent to 2z, and height is equivalent to 2y, we can determine our volume equation is equivalent to 8x, y, z. So, right now we have 3 variables. This is very impossible to do with 3 variables, so we have to do 2 variables. So, r is going to be a constant because it's given to, it's not changing, but x, y, and z are all variables. So we should rewrite our equation with respect to one of these variables. I'm going to pick x. Doesn't really matter which one you use. So, if we take our identity, x squared plus y squared plus z squared is equal to r squared, we can then rearrange it to have x squared equals to r squared minus y squared minus z squared, which then means x is equivalent to the square root of r squared minus y squared minus z squared. We can rewrite our volume equation now with respect to x. This will be the equation we used for a while. Volume is equivalent to 8yz square root of r squared minus y squared minus z squared. So now we have r, which is a constant. We have yz, only 2 variables now. So to solve past this point, we previously mentioned they have to take the derivative and set it equal to 0. The only problem is we have 2 variables, so we can't take the derivative of just one of these variables. We have to use something called a partial derivative. So partial derivative, the symbol looks like this, almost like a d. You have partial derivative of v with respect to, and then you pick your variable. We're going to do y. So the partial derivative, all you have to do is treat everything else like a constant except for your variable. So this is product rule. We have the first function and the second function here. First function, second function. So the first one's going to be equivalent to 8z times the square root of r squared minus y squared minus z squared. And then we have to add this. to what the second one part of the partial will be. We have to take the derivative of this and keep this one constant. So now we have 8yz multiplied by the derivative of this section, which is the equivalent of square root, equivalent to r squared minus y squared minus z squared to the negative 1/2 power. Divide this entire thing by 2. So that's looks like this. So 2. Excuse my bad handwriting. Because that's the derivative of a square root, and then we have to use chain rule and take the derivative of y. So that would be times negative 2y. Okay, so this is our first derivative of this equation, and now all we have to do is do some simplification. This part really isn't that bad as it looks. So what we do here, we're going to take negative 2 and 2, these ones cancel out. So our new equation is going to be the partial derivative of volume with respect to y is equivalent to 8z square root of r squared minus y squared minus z squared plus 8y squared z. Sorry, the minus over here makes us a minus. And then we have to do this divided by the square root of this function. So square root r squared minus y squared minus z squared. We can simplify this further by making a common denominator of the square root. So we can simplify this a little bit further and now say our partial derivative of volume with respect to y is equivalent to 8z times this function, r squared minus y squared minus z squared, minus 8y squared z divided by square root of r squared minus y squared minus z squared. Now, we have this first function. The only problem is we still have two variables. We have z and we have y. So, how do we get rid of one of these variables? We're going to make a system of equations. So, you've probably done in the past a system of equations problem where you have x squared and you have y, and then you have a second equation which is x squared plus 2y, for instance, and they equal different things. And you can use those two equations to determine what they would be. In this same scenario, we're doing the same thing. Because we know optimization requires you to set this equal to 0, we're going to use that as a cool little trick. We're going to take the partial derivative of y, and then we're going to take the partial derivative of z. So we do the same process. I'm not going to rewrite it on the board because it's the same exact thing, except every single variable that's a z here is a y, and every single y variable becomes a z. You just flip them around because it's the exact same process. Nothing changes. So we can get a new equation, which is partial derivative of volume with respect to z would be equivalent to 8y squared r squared y squared z squared minus 8z squared y divided by the square root of r squared minus z squared minus y squared. So now we have our two partial derivatives. We have to simplify just a tad bit. So let's work on simplification. Partial derivative of y. We have dv dy is equivalent to common factor here. We know that we're going to be saying this equal to 0, so we can actually do that right now. This is equivalent to 0. I'll write that here. This is equivalent to, and we can rewrite our equation. So we can do 8z times r squared minus y squared minus z squared minus, and then we have 8y squared z. We divide this whole entire thing by the square root of r squared minus y squared minus z squared. Because this is 0, we can multiply this across and cancel it out. So now we can just have our equation is 8z times r squared minus y squared minus z squared minus 8y squared z is equivalent to 0. From here, we can factor some things out, 8z and 8z. Take 8z, we have r squared minus y squared minus z squared minus, and we factor this out, so minus z, like this. So from here, since it's equal to 0, we can move this across. Now we have 0 is equivalent to r squared minus y squared minus z squared minus z. And you can stop the recording. Alright, we can start. I made a quick mistake here. I factored out 8z and I wrote z again. It should be y squared. So now we know that this should be y squared. And this equation should simplify down to 0 is equivalent to r squared minus 2y squared minus z squared. So much better equation than the other one I just had on math.com. And now we can do the exact same thing for z. Again, same thing, except z's and y's are reversed. So now we have 0 is equivalent to r squared minus, and then we can flip these. So we have 2z squared minus y squared. That's all this would do if I simplified the exact same way. So, now we can take a fun system of equations. We have a constant, which is r squared. So we can rewrite these equations to be in terms of r. So r squared is equal to 2y squared plus z squared. This one should be r squared equals to 2z squared plus y squared here. And now what we can do is set equal to each other. So we have r squared makes it equal. So we have 2y squared plus z squared is equivalent to 2z squared plus y squared, like this. And then from here, we can subtract z squared on this side, subtract z squared, and we can get z squared, subtract y squared on this side, subtract y squared here, and you get y squared. So now we have our equation which says that y squared is equivalent to z squared. This is useful, but we have to actually figure out one of these values is. So now what we can do, we can just change some equations, and then we can set them equal to r, and they can work out what r would be, because this gets rid of the variable r. But this is useful in just a second. So we rewrite it in terms of r, like this, and then we can use some equations, and we can pick a variable. You can use -2 here, for instance, the top part here. So now we have -2r squared is equivalent to 4y squared. Then we have minus 2z squared, and on the bottom we have r squared. R squared is equivalent to 2z squared plus y squared. These factors, when added together, will cancel out. So now we have -3y squared is equivalent to -r squared. We can get rid of these negatives. And now we can say, when we divide this by 3, we're simplifying, divide by 3, and take the square root, and that's y. So, our y value is equivalent to the square root of r squared divided by 3, and our z value is the exact same thing. So z is also equivalent to the square root of r squared divided by 3. Now all we have to do is take our original identity, and we plug these values in. So, y squared is equivalent to r squared divided by 3, z squared is equivalent to the exact same thing, r squared divided by 3, x squared plus equals to r squared. So now I have 2r squared divided by 3 equals r squared. I'm add it to x squared like this. Subtract 2r squared divided by 3. Subtract 2r squared divided by 3. I now have r squared divided by 3 equals to x squared. So x is equivalent to the square root of r squared divided by 3. For those of you who are more perceptive, you realized that the optimization of the volume of a rectangular prism in a sphere is equivalent to a cube. And that's how you optimize the rectangular prism in a sphere.